Welcome back to Differential Equations. In this video, I want to look at phase space for second-order differential equations. This is one of those ideas that really feels goofy until you get used to it, and then you don't know how you ever lived without it. When it comes to second-order differential equations, my application is kinematics. X of t is the position of an object at time t, x prime of t is the speed of the object, x double prime of t is the acceleration of the object at time t, and we let things continue from there. The same ideas will hold for any other second order equations, applications in electric circuits, resistor, capacitor, inductor circuits, are going to give you very similar looking things, and trying to find an analog to position, velocity, and acceleration will help you interpret what's happening here. But let me get my head out of the way and show you exactly what I mean. Right. For the sake of my sanity, I'm going to look at a second order, well, mostly linear, homogeneous differential equation. So I'm going to have something like x double prime of t minus x, let's put a constant there. Let's call that 2 times x prime of t squared plus 9 x of t equals 0. Thinking about kinematics, x of t, that's going to give me some sort of Hooke's law type thing. That is going to give me oscillating motion, some sort of spring. And when we were thinking about that, x prime of t was going to be something related to drag, something trying to slow things down or maybe speed things up based on how fast the object was going. Now, this is very definitely a second order differential equation with one parameter. The key to understanding phase space is to introduce a new parameter, a new function. Let's let y of t equal x prime of t. So my horizontal axis is position, my vertical axis is velocity. And then from here, y prime of t is, of course, x double prime of t. And we can substitute those things into the differential equation. I have that y prime minus 2y squared plus 9x equals 0, which I can rearrange to write as y prime equals 2y squared minus 9x. Then, just rewriting this equation, x prime equals y, there is a dynamical system. And if it is a dynamical system, I can look at its phase portrait. Oops. Let me move that dynamical system just a little bit so that I can still see what's going on and still see the phase portrait. I don't need anything else anymore. All right. Analyzing a phase portrait, I always start by just clicking around a little bit to kind of get a picture of what's happening. I've got some interesting things happening here, I suppose. And then we start analyzing. Finding the equilibrium points on this particular system is incredibly easy because x prime equals y. So that means that y has to be equal to 0. And then that gives us that 2y squared minus 9x equals 0, which is negative 9x equals 0, and x equals 0. The only equilibrium point on this system is the point 0, 0. And if we look at what is happening at 0, 0, we see, well, I guess it's a center, but it's kind of off center. We're building up and we have this kind of sequential shells. So if we just think about tracing along one path on this thing, right? Here's a nice path here. We come downward, we shoot over like this, and we come back upward before we settle down. Now, what do the variables mean? X is position, Y is velocity. So when we are over here, we are a mass on a spring that has been pulled away from the origin, pulled away from its equilibrium point. And when you let it go, it quickly accelerates. But thanks to the drag, it is going faster and not actually moving all that far before it starts to slow down. So it speeds up quickly and then starts to slow down as it moves, and it slows down quite a bit as it moves until it gets to this point over here when it is going to start coming around in the other way. So speeds up, comes towards the equilibrium point, overshoots, comes to a stop on the other side of the equilibrium point before going faster and moving back out and then slowing down once it reaches the far end. It's what you expect to happen. It's kind of messy because it's non-linear drag, but it is kind of what you expect is going to happen. The way this is set up, some weird things happen when you are looking at values of x that get too small. And in fact, what will happen is if you try to start putting these numbers into the system, you are going to find that the algebra starts to give you a differential equation that just looks goofy. So it's not something we really want to worry too much about. All right. Let's take a look at a system that we know a little bit more concretely. All right. Getting rid of the nonlinear term, x double prime of t plus 8x prime of t plus 16x of t equals 0. We know how to solve this differential equation using the method of characteristics. I would like you to actually go and do that. Solve the equation using the method of characteristics, and then graph a representative solution in xt space. So you'll have t on this axis and x on this axis. Then I want you to write a dynamical system for this differential equation by letting x prime equal y and graph that result using phase space so that we can compare a couple of different results. All right. That's a lot of pieces, but hopefully I don't think that they're that bad. There's only one thing that's new and it's fairly straightforward. But take a couple of minutes playing around with all of those things, see what you come up with, and I'll see you in the next video.